So we've actually dealt with inverse functions probably since you started in math in lower school, like second or third grade when you started adding and subtracting. That's an example of an inverse function, addition and subtraction. They cancel each other out. If I add 5 and subtract 5, I get wherever I started. So x plus 5, x plus 5 minus 5 is just x, because I did an inverse function, positive and negative, right? Adding and subtracting. Multiplication and division, they undo each other. So if I multiply by 3, then divide by 3, I'm back where I started, okay? And so we're going to look at inverse relations and inverse functions. The only difference between a relation and a function is that it is in a one-to-one pattern, which we've talked about. So input gives you one and only one output, and that is a function. All right, and so the first definition we have here is if a relation contains the ordered pair AB, its inverse relation contains the ordered pair BA. So when you have inverses of each other, your x's and y's change places. So you'll notice we have this relation here, 318284AB. We've done mapping diagrams. This is my domain, this is my range. If I were to look at the inverse of that, every single one of these just switched x and y's. My 3 and 1 became 1 and 3, 8 and 2 became 2 and 8, and so on. And you'll see in the mapping diagram, now this is my domain for my inverse, and this is my range for my inverse. They literally switch places, all right? A good example is if you have a job, okay? You make $5 an hour. In order to calculate, yeah, I know, long ago. It's below minimum wage. $5 an hour, but I want y'all to do it in your head, so we're going to go with 5. $5 an hour, right? And you want to figure out what your pay is. Well, you would say, well, my pay is going to be $5 per hour, okay? And that's if you know your hours. If we had 8 hours that week, you would make $40, okay? Right? 5 times 8. But let's say I'm doing the other thing, and I want to say, well, my input here is my hours, my output is my pay. If I were to reverse that, and I said, well, how do I figure out how many hours I have? Well, if you want to figure out your hours, you would take your pay and divide by 5. Okay? Now, all of a sudden, your input is your pay, and your output is your hours. Okay? When you have inverses of each other, your input and output change places. Input was hours, output was pay. Input is pay, output is hours. Okay? So now if I said, well, you made $40 this week, how many hours did you work? You would say, well, 40 divided by 5. My output would be hours, 8 hours. Okay? And so that's a very simple explanation of how they switch places. You probably have done it in like a chemistry or a physics, where you need to always solve for the same variable. We did it with literal equations, where you just switch it around so that your input is something different so that you are constantly solving for the same variable. And that's what inverse functions do for each other. Okay, they are literally opposites of each other. Let's look at some relations first. So one thing that they can do with a relation is they can give you a polynomial on a graph. This is just an example. They've given us 4 vertices, 2, 1, 4, 1, 6, 2, and 5, 4. The inverse would switch each places. So now instead of 2, 1, I have 1, 2. And instead of 4, 1, I have 1, 4. Instead of 6, 2, I have 2, 6. And instead of 5, 4, I have 4, 5. What you'll notice is this original relation just mirrored itself over this line. And this is a very specific line. This line is y equals x. I have a slope of 1, up 1 over 1, okay? And I have a y-intercept of 0. Your inverses will always mirror over the line y equals x. So if you have a relation and you find the inverse, if you were to graph that relation, it would mirror itself over that line. That's what inverses do. The reason they do that is because you're switching your x and y. In fact, when we did rotations and reflections in geometry, that's actually how we found them. I would give you a polynomial, and I would say reflected over the line y equals x, and you would switch your x and y's. And that's how you reflected it over that line. That's what inverse relations do. They switch the x and y's. So naturally, the graph of that relation is going to mirror across the line y equals x. So then the other thing that we do with relations, and I'm not going to actually have you graph a lot of them. We're going to be doing more of the algebraic piece of it versus the geometric piece of it. You can find a new rule for relations, okay? Finding a new rule. So to find a new rule, you follow that same pattern. The first thing you do to find a new rule is you switch x and y. You're going to want to know these. Switch x and y, all right? The next thing you do is you solve for y. All right, solve for y. Now I want to look at these two. Do you see a y value? Do you see a y in either of those? No, your y is your output. So in function notation, this guy is your y. You can simply replace your f of x or your g of x or anything of x with y. That means output, all right? And so when we do these, think of that f of x as your y. You're welcome to actually rewrite it as y equals 2x plus 4 if you want to. So let's follow this pattern and find the inverse. My first step is to switch my x and my y. I literally just switch them. I don't switch the coefficients. I switch nothing else except the variables themselves. So instead of y equals 2x plus 4, I'm going to say x equals 2y plus 4. All right. Now I want to solve for y. So my first step in solving for y here is to move that 4 over. So I'm going to move the 4 over. When I do that, it's going to change signs. I now have x minus 4 equals 2y. And then my last step here is to divide everything by 2. Divide everything by 2. So I have 1/2 x minus 2 equals y. All right? I'm going to rewrite this in function notation. The function notation that represents inverse, I'm going to go back to whatever variable type function they gave me, in this case f. And instead of f of x, I'm going to write f, and the notation is this little -1 on top. F inverse. The inverse function of x here is going to be 1/2 x minus 2. Okay? Switch x and y, solve for y. And the last piece of it is just correcting your notation. Let's do one more. So here, I have y equals x squared minus 2. I'm going to switch those. So instead of y equals x squared minus 2, I'm going to say x equals y squared minus 2. My first step, move my 2 over. I now have x plus 2 equals y squared. How do I get rid of a squared? Take the square root of this side, square root of that side. So now I have y by itself, but anytime I take a square root with a variable involved, I have to consider the positive and negative root of what I did. So that is positive and negative root of 2. My final step is just to rewrite my notation. I had a g of x. I'm going to say g inverse of x equals positive and negative root of x plus 2. All right. Questions on finding the inverse. Switch x and y, solve for y. And the last piece is just correcting your notation to show your inverse notation. So the first thing they wanted us to do was plug this in. Then they wanted us to find the inverse and plug in new numbers. All right. I do want to point out, if we had taken 11 and plugged it into our inverse, 8 minus 11 is -3. -3 divided by +3 is -1. So if you had taken all of the y values and plugged it into this new inverse function, you would have gotten all of your x values. So if I would have plugged in -4, 8 minus a -4 is 12, divided by 3 is +4. All right, so that will always work. Your inverse will produce the y to x input output. This is actually from example 2. So example 2, our function was 2x plus 4. That's a y-intercept of 4, a +2 slope. Our inverse was 1/2 x minus 2. So we have a -2 and a +1/2 slope. You'll notice that my function reflected across y equals x, all right? This was my other one. We have x squared minus 2. This is a parabola with a vertex at -2. When I did my inverse, you'll see that my parabola reflected across my y equals x. So you can have an inverse relation that is not necessarily an inverse function. If I were to do the vertical line test over here, my original function and my inverse would pass it, right? I only cross it once. I crossed this blue guy once with my original, the red guy, which is my inverse. However, for this one, my original function passes the vertical line test. That blue parabola, I can draw a vertical line anywhere and it passes. My inverse, however, fails it. Do you see that if I were to draw a vertical line, I would cross this guy more than once, which means the inverse itself is not a function. It is a relation, and it is an inverse relation, but it is not an inverse function. Graphing is one way to tell, do I have a relation or a function? Another way is just, let's use our logic here. My inverse for this guy right here was y equals 1/2 x minus 2. That's a line. All lines other than your vertical, which are an undefined slope, all of the rest of them are functions, okay? You only have one special case that has a problem with a vertical line test for lines. Everything else is going to pass the vertical line test. For this guy, I had y equals positive or negative square root of x plus 2. I can tell you right now that that is going to give me 2 answers if I plug in an x. How do I know that? Because I have a plus minus in front of it. The only thing that won't give me 2 answers is something that makes it 0 in here. -2 gives me 1 answer because the square root of 0 is just 0. But every other number that I put in there is going to give me 2 answers because I have a positive and negative root, okay? So if I put a 7 in here, 7 plus 2 is 9. My answer could be +3 or -3. That tells me right there I have a problem with my output. I should only get one output if it's a function, right? And so graphing, it's one way to tell, but using our skills of will this produce more than one answer, all right? That's going to tell me whether or not I have a function, okay? And really, like, cubed root won't do it. Cubed root's only going to give me one answer because there is no positive and negative root of cubed, right? It follows whatever's inside. But square root's going to be a problem because square root's going to give me a plus minus there, okay? So you don't always have to graph to determine if it is a function. Here's the other part. If a relation and its inverse are functions, then you can take the composite and you will always get x. All right, so remember we did composites for bell work. You took one and you substituted it into another and you got this new function. If you do that with inverses, when you take the composite, it will always give you the answer x. Not x plus 2, not 2x, not x squared. When you do the composite of a function and its inverse, your answer will always be x. And that's how you can tell if 2 things are inverses of each other. So let's look at the example that they give us. They want us to show that g of x and h of x are inverses of each other. This is the only time that order does not matter with composition. If they are inverses of each other, I can do f of g, meaning I can put g into f, or I can do g of f, meaning put f into g, and both of them will give me an x. All right, so let's look at this. Let's try it the first way, and it's h, not f, but that's okay. G of h of x. This means I am going to put h into g. So let's look at this. I'm going to take h. I'm going to substitute it in to my g function. So I'm going to say 4, and instead of x, I'm going to write x plus 1 over 4. That's my x, and then minus 1. So this is basically 4x minus 1. I have substituted my x with my h function. Now all I need to do here is simplify, all right? What happens with these 4? I have a 4 in the numerator and a 4 in the denominator. What can I do with those? 4 over 4 just reduces to 1 over 1, right? Everybody see that? You can cross cancel when you're multiplying. So now I'm left with x plus 1 minus 1. What happens to 1 minus 1? It zeroes out. So now I'm left with just x. Yes, these are inverses of each other. When you take the composite and you get just an x, they are inverses of each other. It would have worked if I had done it the other way. H of g of x. That means I'm going to take g and I'm going to plug it into h. All right? So instead of x plus 1 over 4, I'm going to write 4x minus 1 plus 1 over 4. This is x plus 1 over 4. All right? I just plugged it in. On the top, I have 4x minus 1 plus 1. What happens there? It zeroes out. I'm left with 4x over 4. Can I reduce it? Yes, my 4 over 4 reduces. I'm left with x. Yes, they are inverses of each other. It does not matter which order you do the composite. You should always get x when they are inverses of each other. That should always be your answer. Given that information, given that you know that information, then putting a number into a function and then taking that answer and putting it into the inverse should always yield the original thing you started out with, okay? Because if I take the composite of two functions, this is the composite of my function and its inverse, we're saying you should always get x. So that means if I put a number in here and I take the composite of a number, I should always get the number that I started with. All right? Anytime you take a composite of two functions, you get your x value. Well, this just represents what I'm plugging in for x. So if I know that these are inverses, that these relations and their inverses are functions, then anything I put in to the function with the composite of the inverse will give me what I started with. Always. Always. All right? So if I plug in a number to a function, I take that answer and plug it into the inverse, it will take me back to the number that I started with. All right? That's how inverses work with each other. All right, so I want you to try some. I want you to tell me whether or not these are composite or these are inverses of each other. You may take the composite either direction, it doesn't matter. One way may seem more natural than the other to do it. So, are these inverses of each other? 26 and 28. All right. So just like on that second one that we did, they had a restriction listed there. All right. When you have inverses of each other, your domain may change because you could see that you had a completely different function that was created when you did this. All right. So we have a limitation initially. If we look at h of x, we have a limitation because there is a square root. In real numbers, what can I not have in the square root? Yeah, a negative. So I have to consider, where does this guy hit negatives? Meaning, for initial purposes, this piece has to be greater than or equal to 0. All right? Which means x has to be greater than or equal to 3. That's with my original function. Here they're saying, find the rule for the inverse, and then I want you to give me the inverse's domain and range. And I'm not going to make you do range, but I will make you stick with the domain, okay? So let's look at this. We have this function. They want us to find the rule for the inverse. So how do I do that? I switch x and y, and I solve for y. So instead of having y equals square root of x minus 3, I'm going to have x equals the square root of y minus 3. How do I get rid of a square root? What do I do to both sides? I square it. So I'm going to square this side. I'm going to square that side. I get x squared equals y minus 3. And then my final step is to move that 3 over. All right, so if I were to correct my notation, I'm going to say, well, the inverse of h is going to be x squared plus 3. All right? So then, does this have any limitations? Well, based on this one, no, it does not. All right? However, this is the inverse of a function that did have a limitation. All right? So if I were to graph it, I would graph the original function, which is this guy. He had a limitation, could not be less than 3. So this little function's graph looked like this, right? Well, when I reflect that across, you can see there is a limitation. It is the same limitation that I had before, all right? So here, my domain was that it could not be less than 3. Here, you'll see that it restricts it to it cannot be less than or equal to 0 for my x's now, all right? So you'll see that now my x and y's switched places. Here, when x equaled 3, y equaled 0. So my restriction was x has to be greater than or equal to 3. When I took the inverse, these switched places. This became 0, 3. This was my new limitation. So my limitations actually switched places too. X must be greater than or equal to 0. X must be greater than or equal to 0 here, all right? Because of this limitation that took place right there. So your limitations will follow. Even though I look at this and say, no, that's a perfect parabola, there's no limitations on my input. There actually are, because they follow from your original function. I am talking about the inverse of this function. The inverse of this function has a limitation because the original function did. All right? So when you talk about domain and range, you have to think about what causes a problem initially, and also include any problems that happen when you take the second piece of that. The second piece of it had no problems, so I only had to consider the first part of it. All right? Question.